So today we're talking about this project that is variously known as the UTXO workshop or a Bitcoin-like node. And it started as the UTXO workshop. That's sort of the core of it. And then I saw Nicole working on it recently, and I got pretty excited about it. And I decided, like, hey, what if we make this Bitcoin-like in some ways other than just UTXOs? And she was down for that. So we've been hacking on it for about 2 weeks now. And I guess Nicole's gonna present first and tell us about like specifically the UTXO part and how the workshop works and what a UTXO is and all that good stuff. And then I'll talk about some of the other parts of the node and other ways in which it's Bitcoin-like. So for example, proof of work consensus and issuance that starts at 50 coins a block and has these halvenings like we're gonna have soon in May. And a couple other things.
Okay, so like Joshy mentioned, in this first section, I guess I'll make it a little bit interactive. If you guys went to Sub-Zero last year, you saw the first implementation of this from Dimitri. So the main changes that we did over the past couple of weeks, we refactored about 80% of it. There were 2 security issues that we ended up resolving. So I wanted to walk you guys through that since they're the main changes. But in terms of like the business logic and the UTXO implementation, we're more confident to say that this is in a state now where it can be boilerplate code, or like it could be demoable code that you can give to teams that are potentially looking to build a Bitcoin chain on top of Substrate. If you guys recall that workshop a long time ago, just taking some slides from that a while ago, the 2 main parts to the Substrate stack where this implementation touches is, of course, the runtime module layer. We're building a UTXO.rs module. And then we do a bit of transaction queue reordering and prioritization logic. So if you're new to that really elegant, simple API, we'll quickly walk through what that looks like today as well. Yeah, so over the next 20 minutes, I will walk you guys through the implementation and give you a quick refresher on what UTXO ledgers are. Yeah, so before we do that, maybe we can kick off the interactive part. So the way that we structured the UTXO repo, which you'll find here, is the master branch contains the entire implementation in Joshy and Cecile's latest awesome proof of work implementation. And then there are 2 other branches that accompany like online, offline, asynchronous workshops that anybody can do at any point in time. The branch that you guys want to check out for this seminar is the workshop branch. Yeah, and then you're just sharing the links. Yep. So if you guys can follow along, please do these first few steps. Clone the repo, make sure to check out the workshop branch. And then just to get things building while I walk over the next couple of slides, run cargo test. In the package, you want to run UTXO runtime. Cool. Maybe we give everyone 2 minutes to do that.
Yeah, I'm down.
All right, cool. So quick Bitcoin/UTXO refresher, 2 main ledger models, account space, which is the default that comes with Substrate. And what we're doing here is we've taken out all of those defaults and we want to implement the UTXO ledger model instead. Works a bit like traveler's checks, where you're taking a unspent UTXO or a vector of unspent UTXOs and you are creating new ones via a transaction as you spend those UTXOs.
Cool. So dumb question. What does UTXO stand for?
Yeah, so it stands for unspent transaction outputs. And the analogy is that UTXOs work like traveler's checks in the sense that you could have a traveler's check with a denomination of $100 US, and you can't like cut that traveler's check up into units of 10 each and spend it separately. You have to sort of destroy that entire traveler's check. In this case, Bob has to destroy his UTXO, i.e. 50 Bitcoin, and create completely new UTXOs that represent new values. And you do that through the standard transactions. Cool.
Yeah. Cool.
Yeah, I realize I'm breezing through this stuff a little bit since I'm using slides that usually go into a beginner's workshop. But if you guys have questions, just paste it in the chat or speak up.
Yeah. So what is the difference? Like what is the rationale behind having this model, and how is it? Because like to me, the account-based thing makes a lot more sense.
Yeah. So
this is, I guess, yeah. Go.
This is cool for a couple of reasons. As you'll see in the demo later, you can, so the whole thing that makes Bitcoin cool is that in a single transaction, you can actually spend UTXOs that have different owners. So in our ecosystem, in a demo that we'll go through shortly, you can see that we can spend these things in unsigned transactions. And at a certain point, when you spend things, it can be gasless. It's also cool because it demonstrates the power of Substrate in the sense that you don't have to stick to one ledger accounting model. You can have various things. It's also cool because I think when Dimitri originally came up with the implementation, he had a good point in that it demonstrated that you can just very easily, within 5 to 10 lines, change your transaction pool ordering logic as well. And so if you built like a cryptocurrency blockchain, you could very easily, in very few lines, like implement any type of ledger model. Yeah, but to me, I think the most cool thing is just you can spend UTXOs with different owners in unsigned transactions and seed a bunch of accounts with UTXOs and essentially not have like the gas onboarding friction that chains like Ethereum has.
Yeah. Another thing that I like about the UTXO model is that it allows a lot of concurrency at the transaction level.
Mm-hmm.
So like in Bitcoin and in this thing we built, we don't really fully get to take advantage of that. But in the accounts-based model, basically we have this mapping between like, you know, some notion of account ID and then like the token balance of that account. So, you know, it would be like Joshy has 10 tokens, Dan has 5, Kian has 100, and et cetera, et cetera. And so if I like make a couple spend transactions in a row, we have to execute them in the proper order because at some point I'm going to run out of balance. And after that point, then my spends are invalid. But with the UTXO model, each transaction explicitly references which inputs it consumes. So there isn't any fixed ordering about like that those transactions have to be executed in. So they can be reprioritized based on like, okay, maybe this one came later, but it has a higher fee, so it's going to get included in a block sooner or something like that.
Yeah. Cool. Okay, so if you guys have cloned it, I think this is the part where you can easily follow along. Open up UTXO.rs, which is our main module implementation. So wanted to walk you guys through how we structured how we're representing transactions and unspent outputs in our state. And it's actually pretty parity with like feature parity, even the naming in terms of how Bitcoin does things. Yeah, so at the very fundamental level, there's the representation of a single UTXO, and that's declared here. If you guys are following along, starting at line 62. The naming value is, of course, the value of the UTXO. The pub key designates the public key of the owner, i.e. the person who can later submit a proof or a signature authorizing the spend of this UTXO. So the value and the owner. And then what's more interesting is how we've structured UTXO transaction, the representation of that, and that's where most of the changes are. So what is in a UTXO transaction? What is being created when Alice wants to submit a transaction to Bob? Yeah, so, I'm responding to Surag's question. If you've joined within the last 5 minutes, this is a interactive seminar. Where there's like a 5 to 10 minute workshop component. So as we walk through the explanation of UTXO, please go to this repo. Get the workshop brand, and then start building it by running the test. Sure. All right, cool. So what is in a transaction? What happens behind the scenes when you're spending a UTXO? Well, you're creating more transaction outputs, going back to the traveler's check analogy that we were talking about. And later in our implementation, we do all the security checks to make sure that the values are still accurate, not overflowing, underflowing, etc. I think what's more interesting to point out is the latest change in what's going into the transaction input. So previously, I don't know if you guys recall, but we had a critical vulnerability to front running where this SIG script, meaning the proof, and this is what it's called in Bitcoin as well. In Bitcoin, this SIG script signs over the previous transaction hash where this UTXO that, say, Alice is trying to spend now was originally created. But in our implementation, since we're taking advantage of having like a state and having a construction of a place where we can save our unspent outputs, we had a vulnerability where if the user just submitted a signature to authorize this transaction input, it meant that any malicious node can just anyhow change the transaction outputs. And then going back to Joshy's point, reprioritize the transaction to push the malicious transaction through and effectively repoint all of the new UTXO outputs to himself, which is kind of a critical issue. Anyway, so this new implementation essentially does something where...
Can I make sure I get the old, make sure I understand the old design and the problem with it? Because I think I do now that you told me about it and showed me the code, but I actually was at the workshop originally and I didn't see the problem. It took me a long time to see the problem. So the old, more naive design is basically like, if you are a user of this chain, you have a bunch of these unspent transaction outputs, and now you want to spend some of them. So maybe like I want to buy something that costs 70 tokens. So I gather up, enough UTXOs that I own that they add up to at least 70 tokens or maybe a little more. And so in order to let the chain and all the validators or miners know that I can spend these UTXOs, I have to sign each one of them. And
Correct.
So like, and this is the old design I'm talking about. And so like, okay, so fine. So I sign each one of these transaction outputs I want to spend. And then I take those signatures and I take the new outputs that I want to create and I make them into a transaction and I send it to the chain. And like, if no one's being evil, then fine, that goes through and everything works. But I think we all know that Dan is evil. So like, if he's one of the miners, he might get my transaction and he'll be like, okay, let me take this thing apart, because I know the first couple parts are Joshy's valid signatures over his UTXOs. And he can't create those signatures, but I've created them. So he keeps those. And then instead of creating the new outputs that I wanted to create, where they go to like whatever I'm actually trying to buy or whomever I'm trying to pay, he like replaces just the newly created ones with his like malicious outputs that send the tokens to him. And the reason that works is because I only signed over like the individual inputs that I was trying to spend. So is that the correct bad design or the old design?
So the previous old design, and this is how we're representing transaction inputs. So going back a few steps, outpoint is essentially the address /hash in storage, where we are storing previous and available unspent outputs. So the previous implementation, this SIG script here, only contained a signature from the owner of this UTXO, where he or she just signed over this outpoint. And so there was nothing tying that intent and the fact that the owner is authorizing, or so I think the other way to rephrase it and to look at it is the old implementation, the owner was only authorizing to spend this existing UTXO. He wasn't securing and ensuring transaction integrity with the output that he wanted generated. Yeah, and so that's kind of a big hint. I think the solution was quite straightforward. At this point, does anyone want to posit what a easy solution to this would be? Like how would the spenders try to ensure the entire transaction integrity and lock in place the designated transaction outputs?
Maybe you just hash all of it.
Yeah, absolutely. which is what turns out Bitcoin actually does. And so our old implementation, we changed a lot of things. And so actually the elegant solution is to revert back to more feature parity with Bitcoin. Yeah, so this new implementation very simply just signs over the entire transaction, but there's kind of like a impossible thing here where you can't sign it with the SIG script already generated. And so what we're doing is we're stripping out this SIG script, which is a H512 hash, and we're just signing it where you can imagine this field is a bunch of zeros, right? And where there's a point where when you submit the transaction, all of the UTXO owners provide their own signatures. And so this is where you get the functionality where within a single transaction, you can actually still spend UTXOs technically owned by Alice and technically owned by Bob. So meaning when this transaction is being constructed before it's sent to any nodes, Alex is going to take this desired transaction, sign everything, inject, post-inject her SIG script proof here. Bob will do the same thing. And then with this completed transaction, they have a valid transaction. Does that make sense so far?
Is that in Bitcoin? Is that how people would normally construct transactions containing UTXOs from different owners? Like they would prepare them sort of offline somehow and then bundle it up, and then when everybody's done and signed it for, it's sent over.
Yeah, correct. With the main key difference where we're still signing over this out point, which is the address hash for where we're storing these unspent UTXOs in state. Whereas Bitcoin, it references previous transactions where a UTXO was created. All right, cool. So that was a quick primer of UTXO. Are you guys, are you building? Are you finished building? Are tests failing? Because if so, that's good. It's a part of the workshop.
Maybe.
Yeah.
Okay,
cool.
Okay.
You should be getting, if you're on the workshop branch, you should be getting build errors. Since it's a part of the workshop, I guess, to get people to step through the implementation and resolve those errors. If you are building the master branch, everything should be working. Yeah, you should be getting build errors too. I took out some imports and I introduced some syntax issues intended for whoever's learning about Substrate for the first time to go through our documentation. There should be comments that say to do that hint at where the fixes should be. So feel free to, during the seminar, also like synchronously fix those things. And I'm mostly interested, since I'm seeing most of the attendees for the seminar are parity folks, I'm mostly interested in getting your feedback about this, whether or not there are parts to it that we can improve.
So Nicole, I lost your audio just for a second there. You're gonna walk us through a demo, I guess?
Yes, yeah,
Okay, cool.
I'll walk you through a demo in Polkadot apps, just to kind of demonstrate the use case that we just walked through. Okay, cool. I have some pretty helpful printouts for walking us through the demo, because that one step where you're signing over a transaction, which is actually formally called a simple transaction, where all of those SIG scripts are carved out, that step is kind of annoying. So I printed out some helpful things here. And the way to see how this works. Yeah. So in ChainSpec, I think we designated a seed UTXO for Alice. So she should already own something of value 100. And I've also calculated the hash where that UTXO should be stored. So let's just check in our chain state that that is the case. Yeah, so this key, if you guys verify the key, actually is to Alice, and this is her Genesis UTXO that we've seeded her with. Cool. So then the next thing is suppose Alice wants to send then 50 UTXOs to Bob, and then the remaining amount she will send to validators. So I've also pre-constructed what the encode and the hash for that would look like. Similarly, let's go to the UTXO model.
Okay. How about this? I'm guessing she'll be back with us in a second, but I also have the demo prepared, so I think I can show it. Can you guys see my screen now?
Yep.
Okay, cool. So let's see. So I'm on master branch here. I think she was too. And just as like an easy way to tell, if you get the emojis, that means you're on the latest thing. This is something that just came in Substrate Alpha 2.0 Alpha 6. So it's also like a convenient indicator for how new of a substrate you're using. So yeah, so it's called UTXO Workshop, and I'll do just like she did, and we'll purge the dev chain. Okay, cool. So we've got a clean state, and then we'll run the dev node. And so, yeah, so this looks good. Basically, we have a node that's just running. You know, we can see blocks are getting mined. And then Nicole was saying this. I don't know if it came through because it was getting a little choppy. These like helper inputs here are just information that tells people who are doing this exact demo, like some of the signatures and stuff, so that instead of generating these for ourselves, we can just use them. So,
Hello, can you hear me again?
hi, yeah, you're back, Nicole. Sounds good.
Okay.
I was just sort of starting to show the same demo. Do you want to walk us through, and I'll screen share so you don't have to send so much bandwidth?
Yes, that is a great idea. Sorry, guys. I'm competing for bandwidth with two other devs who are working on the same time zone as Berlin. So
yeah, cool. Okay, so we've got our blockchain running, and I know you were talking a little bit about the Genesis state, so I was just gonna show our chain spec file. And you know, there's a lot in here. We won't look at all of it, but there's this testnet Genesis function, and this is what configures the initial state. Like, you know, I purged the chain, so we're starting with a brand new state. So here's where those helper lines came from. They're printed out right here, and specifically, this is the part that sets up the Genesis state of the UTXOs. So basically, we pass in this parameter called endowed UTXOs. It's just a vector or like a list of public keys. And so then we iterate through that list, and we say for each key in that list, we give them a new UTXO with a value 100. And of course, the pub key is the thing that we passed in. And so we called this thing right here. We just gave Alice as the only one. So we have one Genesis UTXO, belongs to Alice, and Nicole has conveniently prepared all of this data for us to use. So do you want to do the UI part, Nicole, or is that where we were?
sure.
Okay,
Yeah,
cool.
I'll narrate as you input in the parameter.
Oh, perfect. Okay, that sounds good.
Okay, cool. Yeah, so the simple demo is just Alice is spending her Genesis UTXO of value 100, and she is splitting that up into one UTXO designated for Bob of value 50. And for the remaining amount, the remaining 50, in the implementation, if you guys go to a function called disperse rewards, you'll see that we've actually implemented that such that any transaction remainder goes to reward validators.
Let me show it. Here, is this the one you mean?
Yes, correct.
Yeah, cool. Okay, so it's going to take in the block author, so like whoever mined that block, and then we read the reward out of state, which I guess we can talk about shortly, and then we create a new UTXO where the value is just like whatever value had been accumulated, and we set it, we assign it to the author, whoever authored the block.
Yep, and then we calculate the hash for the new UTXO.
So Alice is going to be generous and give like half of her 100 tokens to the miners, I guess, right?
Yeah, correct. And then later on in our transaction prioritization, you'll see that this remainder value amount is the value that goes into the transaction priority, right? So the bigger tip you leave your validators, the higher in priority your transaction makes it in the transaction pool.
Yeah, cool. Okay, so to construct this, I guess like, you know, I can add as many of these inputs as I want. Like we can consume a whole bunch of UTXOs, but I think in this case, we only want to spend a single one, right?
Yeah, correct. So we will point the input to Alex's Genesis UTXO, and then the output, let's create a single UTXO, value 50, pointed at Bob's pub key.
Okay, cool. So that's the Genesis one. And
Yep.
then, so we need Alice to sign, really she's signing over this whole transaction, but I think you've handled that already, right? So you gave us the signature over the whole transaction. Ooh, let's see if I can copy it all. Boom. Boom. Okay, and then the question is like, where are we sending all these outputs? So we'll send 50 to Bob, and here's Bob's public key.
Yeah, and you guys can easily follow along in all of these steps. I'll paste the repo link here again. All of these instructions are very clearly detailed in the README in the GitHub repo.
Yeah, maybe I'll just show that too. So in the repo, not very far down the README is the UI demo. And so it also has all the same, like those values that I copied from my terminal, those are also present here, so you can get them that way. Okay. Okay, so Nicole, question for you. I know because we practiced that I'm going to submit this unsigned, but my first instinct was that I need to sign the transaction as Alice. So what's up with that? Why is it unsigned?
Yeah, we thought it could be like a neat touch in that in the Bitcoin model, you're signing over the transaction itself, and you're signing over a proof that authorizes the spend of a UTXO. And so by definition, that signature for each input UTXO that you want to spend could come from their respective owners. It could come from different owners. And whoever actually pushes this final transaction to the network should theoretically be anyone. And that's kind of how Bitcoin works. Yeah. And so I think it was kind of cute here that we can now submit this transaction unsigned, in that you technically don't need to select the selected account Alice, which I think also has like sudo and other permissions as a default, that anyone can really submit this transaction.
Yeah, I didn't even really think of that. So like Alice has created her signature here. It doesn't matter who sends this to the chain. So like Bob can send it and it should still go.
Yeah. And correct me if I'm wrong, guys, but submitting an unsigned transaction, you don't need gas, right? Do we?
Yeah. Yeah, it can't charge fees because it does. Oh, is that true? I think you're right.
I remember reading that somewhere, but I could be totally wrong. If I'm right, then I think this is a cool demonstration of, again, the fact that like this is now a more frictionless token implementation than the accounts or Ethereum model, where any new account needs some starter gas to get things going.
Yeah. Okay, cool. So that went in. We saw the events and everything. So we should be able to check, like, if we take this same output that Alice just spent, we should see that it's no longer in chain state. Yeah, perfect. Cool.
Cool. Yeah.
Did you want to show code, or where did you want to head next?
Yeah. So I think at this point, maybe I can take another 7 minutes and walk through the more interesting parts of the code. And then I think we're in a place where everyone can independently approach this workshop if you so wish, or maybe to improve it by a lot. So Joshy, would you actually mind showing code? I don't think I.
Oh, sure. Yeah. I thought you were saying you wanted to show. Yeah, I'd be happy to. Okay, cool. Yeah, here we go. Do you want to be on the workshop branch?
We can be on the master branch, actually.
Okay.
The master branch, again, contains the full implementation. The workshop branch contains a couple of bugs since the workshop is you get to treasure hunt for things.
Okay, cool. So here we are. We're in the UTXO palette. So
Okay,
what do
cool.
you see?
If we can flip to the validate transactions function. Yeah, cool. Yeah, so this is where we're performing most of the security checks to ensure that this UTXO transaction the user is trying to make is valid. You can see we check for basic requirements, transaction inputs, outputs exist. We check for things like the total number of outputs should not exceed inputs. What's a bit peculiar about this transaction is that it's actually getting called at 2 places. First is during the transaction pool check stage itself. So before where the state transition happens. And what we're doing here is actually accounting for a race condition. So consider a case, and this happens a lot in Bitcoin, which makes it kind of annoying to use. Consider a case where you have sent, where Joshy has sent Keon UTXO-A, and Keon now wants to spend UTXO-A to Hernando. I think given normal network latency and other race conditions, it's very possible that by the time that Keon submits his transaction, several nodes have not heard of the input UTXO that he's trying to spend. And so this validation function also checks for that race condition, and it populates a missing UTXO vector in line 201. And so this function will return a valid transaction result, as you can see in the function signature, in 2 cases, where the first case is there's no race condition and the transaction is valid. And the second valid result case is actually the transaction is valid, but there may be some missing UTXO. So now
am I showing the part that you wanted? Am I showing the part you wanted to see?
Yes, you are. Yeah. So this is where we're constructing the missing UTXOs. It's where we're iterating through the inputs in transaction inputs and checking whether or not those UTXOs that we're trying to spend.
Okay,
Yeah?
Cool. This part, right? Oh, I see what you're saying. Okay, so we just make this empty VAC, and now we're gonna go see if we need to actually we're gonna loop through all the inputs to this transaction, and if any of them are missing, we're gonna put them in this VAC.
Correct. Yeah.
Okay, cool.
And then all of this gets constructed into a special substrate struct called valid transaction or transaction validity. If you scroll down a little bit further, starting at line 236. Yeah. So I thought whoever wrote this and designed this in Substrate was awesome because this makes reordering transaction pools so much easier. It has the following states that you can set. So requires will look for taking a step back. So the moment your transaction hits the transaction pool, you can actually check for what type of transaction it is. And in our case, we're checking, hey, is the user trying to call the spend extrinsic and spend a UTXO? And the place where we're checking for this, if you flip to lib.rs,
so this is like a transaction pools runtime API, I think, this part?
Correct. Yeah, so this part. In line 331, you can see that we're checking to see if this particular incoming extrinsic is of type spend in call. And then we're actually calling this validate transaction function in our UTXO module.
Okay. So this is like the main runtime file. This is where all the different runtime logic is aggregated together into one. And so we're saying if it's this particular kind of transaction that spends UTXOs, we have a function that prioritizes them and checks their validity, and we want to use it. And then I get this is the part that I think is cool. The idea is okay, if it's not one of those, if it's just some other transaction, do it the normal frame way, which is to just say they all have equal priority and they have to be applied in order of increasing account nonce. So that this is the one that I was saying isn't very concurrent, and then this one that Nicole's describing is the cooler UTXO one. Did you want to, let's see, do we want to go back here?
Yes. Okay, cool. So in this function, we are configuring certain parameters around this transaction. Namely, we're giving it these tags called requires and provides tags. And within the transaction pool, if a new transaction comes in, you can look at this particular transaction type's requires tags. And if those tags are missing, this transaction just won't be processed. So in this case, we can very easily just use our missing UTXO hashes when there's a race condition, right? And adding that to the requires tags. And of course, when a transaction does go through, then it fulfills provides tags, and that the new UTXOs that are created thanks to this new transaction, those hashes could become the requires tags for future transactions that are going to spend those UTXOs. That was kind of a mouthful, but it's kind of straightforward to reason about. And then going back to our previous point where in this implementation, we designated the transaction reward, so the remainder amount that would otherwise be burnt from this, from the total sum of the input UTXOs, we're also using that reward, dispersing it to the validators, and using that to designate the priority of the transaction.
Yeah, cool. I think that's really, this part is really cool and very Bitcoiny, because it's like the miners are incentivized to mine the transactions that have the highest reward for them. So like as a user of the chain, you know, I make a transaction, it consumes some inputs, it creates some outputs, and the discrepancy between the input value and the output value is the reward for the miner. So when the miners run this code, because of this priority line right here, they're doing exactly that. They're saying like, okay, well, this transaction only leaves half a token for me, and this other transaction leaves one whole token for me. So I want to prioritize that higher. So like if the block gets full or runs out of weight, I want to make sure I have the ones that are going to reward me most generously in my block. So I think that's kind of cool.
Yeah, and last but not least, longevity propagate. Longevity is transaction longevity, just how long a transaction will stay in the queue before it expires and is deleted from the pool. And then propagate is whether or not I think a node would propagate a particular transaction to others. And I think the default is usually true. So that's what you see there.
Yeah, nice.
Yeah. So lastly, the actual kind of runtime logic place where this function gets called is in the actual spend extrinsic, which is our external function. So Joshy, if you scroll a little bit ways up. Yeah. So as you can see here in line 110, we call validate transaction again. It'll still return a result wrapped around a valid transaction. And here we're just using it to get the priority and passing that into update storage, which does all of our state updates and actually writes the new UTXOs to state, as well as disperses the validator rewards. Cool.
Yeah, cool.
I think that's it. Those were all the components I wanted to highlight. Did I miss anything, Joshy?
That was really good. I was gonna maybe take a peek at this. I don't remember if there's much interesting in update storage, but yeah, this is the one I think where we like pull the spent UTXOs out of storage and put the new ones back in. I couldn't remember what this second parameter was for though.
Yeah, so that since we already calculated the validator reward value in validate transactions, and I want to minimize the amount of times that we iterate over the vector inputs and outputs. So here I'm just passing in an already calculated validator reward.
Okay.
Which update storage will use to create new UTXOs for the validators.
Yeah, okay, that makes sense. So yeah, let's look at that one. I also think Nicole did a cool thing here, which is like abstract this out into a helper function. And it's cool, like obviously helper functions are always cool from like a modular design perspective. And they're particularly cool in Substrate because you don't always get great error messages when you're inside these macros. So like you can imagine when you're coding something like this, you might have like a syntax error or like a weird borrow check error or whatever. And like if you do it in a helper function, you get the normal Rust C compiler errors and messages instead of the like originates in a macro outside the crate. Good luck. So, okay, yeah. So here it is. Oh yeah. So
that was retreat. That was cool. Yeah.
Oh yeah. Okay. Cool. So this is the part that I was forgetting. I think like we have this storage value called reward total, and so like, yeah, I guess we're saying the new total is whatever it used to be, like read the value out of storage and then add whatever the reward for this particular transaction was and write it back into storage. Yeah, cool. So yeah, so let's see, I guess like maybe is this a good time for me to talk about the other Bitcoin-y parts of the node? Do we still have Nicole? Oh, cool. Okay, so we've looked at the transaction, like processing of individual transactions, and we just saw how each transaction adds a little bit, or well, I should say like 0 or more tokens onto this accumulating reward. And so at the end of the block, we use this onFinalize method, and this comes just, it's part of frame, any frame pallet can use this onFinalize method, and this code executes at the end of the block. And so basically what it does is it uses this block author trait, which I'm going to talk about in due course, but not quite yet. But basically this block author trait allows us to retrieve the author of the block, and if it's none, then fine, we just deposit this event called rewards wasted. That's it. And those rewards go nowhere. And otherwise, if we do provide an author, like if whoever mined this block had used the flag to pass in their proper authoring key, then we go down into that disperse rewards function. So again, just calling a helper function. So let me find that one. Here we go. Okay. So you can see disperse rewards takes in an author, because if we didn't have an author, we're not even calling this. We're just saying they're wasted.
Hey, I don't know if you guys can hear me, but that was the gist of it.
Cool.
I am
yeah, sounds good.
Using my internet.
We hear you now. Okay, so we read the reward value out of that storage item that we were talking about, and the reward value is made up of 2 parts. So there's the one part we talked about, which is where you add up all the individual rewards from each transaction. So, you know, one transaction offers a token, another transaction offers half a token, and there's all these transactions, and those like little transaction fees just add up. And then the second part of the reward is this part here, which I get through the issuance trait, which I'll also talk about shortly. And this is the thing that we've modeled it after Bitcoin, where like in the first handful of blocks, it's 50 tokens that are issued out of nowhere. They didn't come from someone. They're just minted per block. So like if you're the person who mines the first block, you get these 50 tokens plus however many tokens come from regular transaction fees. And then same for the second and third and fourth block. And eventually, when the chain gets long enough, we have one of these things called the halvening. So has anyone heard of the Bitcoin halvening? Yeah, cool. So the halvening is a thing that's coming up soon, like in the real live Bitcoin network. I think like maybe May 10th or 12th or something is the tentative date. And the rewards get cut in half. So after that number of blocks, then this issuance trait will start returning only 12.5 tokens per block. And then after another period goes by, then it'll be down to like 6.25 tokens. And so the particular implementation of this issuance trait that we have is that one where there's the halvenings and it sort of decays exponentially. We'll look at that trait and other ways to implement it shortly, but for now, okay, so we've got the reward value. So we make a new UTXO. It's just the value we just talked about, and it goes to the author. And then we do the normal stuff where you like calculate the UTXO hash and you put it into the state where we're keeping track of the UTXOs. And instead of the rewards wasted event, this time we're doing the rewards issued event. Yeah. So maybe I'll just pause there for any questions or comments or anything. And questions are totally welcome and encouraged. Oh, we've got some in the chat, I see. Let's see. Oh yeah, please go through the workshop, totally. Yeah. Okay, cool. Who wants to ask a question or something? Who's brave? Oh, Cecile's here. Hello.
Hey,
Good to see you again.
thanks, me too.
Okay, well, since I noticed you're here, maybe I'll follow up about the part that we talked about last week. So I'm going to work from the inside of the node out. Actually, this is a good time to show this diagram. So the whole pink thing is our Bitcoin-like node, and the green box is the runtime, and that's what we've been talking about so far. And mostly we've been talking about this UTXO pallet right here. And Nicole already explained how it interfaces with the transaction pool through the transaction pool API. So we've covered all of this part. So what I want to talk about now is this block author trait. So we just saw that we need a way to get the block author so that we can like issue the rewards to them. So let's take, here we go. So in my runtime, I have all these different files, like the librs is the main one that aggregates all the logic together. And then the UTXO one is the one we talked about for a while. So let me just show in this main runtime aggregation file. If you've ever written a frame runtime, you'll definitely recognize construct runtime. And if you haven't, that's fine too. But basically what construct runtime does is it takes all these different pieces of logic that we call pallets, and it puts them together in your runtime. So here's UTXO, here's block author. And so once we have all these pallets in our runtime, we can wire them together. And so you can see that here, this trait that's necessary for our UTXO pallet, it has a couple dependencies. The first one's not that exciting. It's just like, it's this event type. The comments usually call it like the ubiquitous event type, and it's just needed if you want to emit any events. So like, many of them have it, like, sudo has it for sure. The regular old balances palette, which is still in our runtime but totally separate, has it. So that one's not too interesting. But our UTXO trait also has a couple other associated type dependencies. So like this one is called block author and this one is called issuance, and we'll look at both of them. And so basically it means if you want to use this UTXO palette, you have to give me something that can tell me the block author. I don't care how it's implemented or how it works. It just needs to tell me the block author. And likewise, you need to give me some type that will describe how the issuance is supposed to work. I don't care what the issuance is. I don't care if it's infinite. I don't care what your monetary policy is. I just need something that can tell me the issuance. So we'll just take a look at both of those. And so for block author, I wired it up to this other palette that's also called block author, and I'll show it to you. So now we're in the block author file, and I guess I want to start right here. So I made this trait, and it only has a single function called block author. It takes no parameters, and it gives me back an option for a public key, and that public key, if it exists, should represent, well, the block author. Okay, fine. So what are some ways we can implement that? Well, here's a dead simple one. And it's it's kind of like a pattern in Substrate that if you have one of these associated types, and there's some way to like turn it off. Like, you could imagine someone building a chain saying like, okay, I want to use your UTXO palette, but like, I don't really care about finding the block author. Maybe I'm just not doing block rewards or for whatever reason. So in that case, you can use this empty tuple, or I like to pronounce it unit. So we implement this block author trait for unit in like the most trivial way ever. And we say like, hey, you have to give back an option. Great. Just give back none every single time. So if we wanted to use that and we wanted to say like, hey, no block authoring, then here in our runtime aggregation file, here's the part we were looking at where we implement our UTXO trait. Then I could just do this. I could just say like type block author is unit. And now we don't ever provide a block author and we don't get any block rewards, and that's totally fine, and it compiles. That's not very Bitcoin-like though, because Bitcoin does have block rewards. And so let me show you how I wired that up. Okay, right, so here's the trait, here's the trivial implementation, and here's the implementation for our actual block author palette. And so what it does is it reads the author out of this storage item. And so like, let me just show you our storage items. Here's where we declare the storage items. That's what the decal storage macro is for. And this part is basically just boilerplate syntax. I'm not going to talk about it. But I create a single storage item called author, and it stores, as you'd expect, an option for a public key. So when something calls into this pallet saying, hey, give me the block author, all it does is it reads that value out of this storage item. Now, what we don't want is for like somebody to author a block and get their key in this author item, and then like maybe the next block, the author doesn't bother to supply their key. Well, we don't want the old previous block author's key to still be kicking around in here, like reaping all the benefits of all these other blocks. So we do this thing called onInitialize. So like in UTXO palette, we used onFinalize, which runs at the end of the block. Well, here we're using onInitialize, which just does this simple thing, which is kill this author storage item. So it basically says like, hey, whatever's stored in there, set it back to none. Okay. So the final piece of the puzzle, the final question is like, well, how the hell do we ever get an author in that storage item in the first place? And that happens using a particular kind of extrinsic that's called an inherent. So an inherent is a thing that whoever authors the block gets to put in the block. It's an extrinsic, which means it's kind of like a transaction. And other places you might have seen this is like the timestamp. So every block has a timestamp that the author gets to put in. And so here's where I wire that up. You always have to start by giving your inherent a unique identifier, and it has to be exactly 8 characters long. So I just call it author, and then I gave it some underscores to get it up to the 8-character requirement. There's some stuff about inherent errors, like, you know, this is important and it has to be there. It's not like particularly interesting, so I'm not gonna talk about it now. You can copy it from here, or you can copy it from the timestamp palette. Here's the part where it actually does get sort of interesting. So I make this type called inherent type, and basically what this says is, okay, so you're going to provide an inherent. What type of data is coming in with this inherent? So it might have been the timestamp. It might have been an actual public key. Here I'm doing this thing where I make it like an opaque type. So it's just a vector of bytes. And as the comment says, we're going to decode it into the actual public key in a little bit. So we make this structure. It's called inherent data provider, and it has one piece of data with it, which is this vec U8. Okay, fine. And so now we have to implement this, this provide inherent data trait. So anytime you're writing an inherent, you do this. It happens in the timestamp inherent. It happens here. Like this one's totally straightforward. It just gives back the inherent identifier. That's the author underscore underscore that I created like way up here. So fine, that one's done. Let's see, provide inherent data. I don't even honestly remember how that works or where I saw that example. So I did this. I called inherent data dot, which is the thing that comes in, dot put data, and I give it, so I associate it with the inherent identifier. That's the author underscore underscore, and self.0, that's this thing. That's my vec of bytes. Okay, so this is like a pretty, what's the word, like vanilla implementation of this provide inherent data trait. You know, like I think I probably copied it from timestamp palette. Okay, and then the final part, this one, provide inherent for module T. So this is where we actually give the instructions for how to create one of these. So it's like, okay, you're running a mining node and your author, like you're gonna put your author key in there. Here's how you do it. So we say like, let author raw equal data.getData. So that's the thing that came from up here. That's like the raw vec of bytes. And we decode it to a public key right here. So now instead of being a vec of bytes, it's actually decoded into a proper, like, you know, SR25519 public key. And finally, we make this call to the set author extrinsic, and that is up in my decal module right here, set author. You can see it's an inherent because I did this ensure none. That means it's not like a signed transaction. It's not a root transaction. So we start by making sure that there is not yet an author set. And if there is, then we error out with author already set. So this would happen like if you somehow had 2 of these inherents in the same block, which is illegal. And so in that case, it errors. But assuming everything went okay, then this is where we actually set the storage item to be the author. So the flow was like, starting at the outside, you mine a block, you put in one of these inherents that has a serialized public key, then we decode that serialized public key into an actual like public key type, and then we put it in storage here. And then our UTXO palette, when it's dispersing rewards, it will use that block author trait, and it will grab the block author from the block author palette. So let me pause there, and I'll take any kind of questions or comments, either like very specific ones about code or just general architecture ones or whatever. Kian, what's up?
Yeah, so these inherents, where are they validated? Because can someone, yeah, where's their validation?
Yeah. So there's yeah. So let me show you that. It's implicit in the one that I just showed you. So it happens in this trait, the provide inherent trait, and there's this required method called create inherent. And let me just show the docs for this thing. That's not it. Okay.
So I can elaborate a bit more while you're looking at it, because the function, the dispatchable itself only had check ensure none, which basically is no requirement. Anyone can call it. How can we prevent someone else from just saying, "Yo, I'm
well,
the author"?
ensure none doesn't mean anyone can call it. It means it has to be one of these inherents. It can't be assigned.
Ah, okay.
Yeah.
Okay.
So the only person who can call it is the block author themselves.
Are we sure? Okay, I'm not sure. But
I was sure until you gave me doubts. So
okay.
let's just check some more docs. So here's ensure none. Ensure that origin O represents an unsigned extrinsic, returns OK or error. Oh, so there's also this thing, unsigned transactions. Like, oh, yeah, in fact, we saw those when we were spending UTXOs. So,
and there was like a report today from some blog in Kusama where someone tried to set the timestamp, for example, and it failed, of course. But I just wonder, like, how and what caused it to fail? Because it was exactly this. There was one block in Kusama, and someone reported that it has two timestamp.sets. One of them was some random guy trying to submit it. We also don't know who that person is because it's not signed.
Yeah, right. Yeah. That's interesting. So like the normal, like the happy path for setting timestamps in Kusama is like the block author, whoever it is, puts in that inherent, and there's only one per block, and that's it. But you're saying it sounds like someone else also made that call manually.
Yeah, I mean it failed, but I'm not sure how it failed, and I'm also not sure how this will fail. I mean, this is probably also safe what you're showing. Like not anyone can claim that they're author, but I'm not sure how.
Yeah, now that you ask it, it makes me wonder. So let's actually do an experiment and just try to do it. Okay. So I booted up the node again, and then we can come back to the UI. And I think the errors are just these ones that it couldn't connect because my node was down. So let's just make sure I get a new block. Yeah, great. We're getting blocks. So extrinsics, block author, set author. And I think I just need 32 bytes here. So let's just put them in.
Yeah.
Boom.
Oh, that's signed. Okay.
Oh, I didn't mean to do that. Definitely.
But you should send it as unsigned.
Yeah, that was never going to work. Invalid transaction stale.
Okay, yeah, that's coming from somewhere, but I don't know.
Yeah, it failed somehow. I don't know exactly if that was the way I wanted, or if it is just like unknown transaction validity, no unsigned validator. That probably is more like what I was thinking would happen.
Okay. So maybe these inherents cannot be submitted externally. I'm not sure. I will check it out definitely, and I'll let you know. But yeah, because that error means that it's trying to go through the unsigned transaction path, and this is different from inherent path. They're very similar, unsigned transaction and inherents, but they're different.
Yeah. Okay. So unsigned transaction is what we were using to spend UTXOs. Those are really transactions. They're not supposed to come like from the author or whatever.
Yeah.
So, okay, so let me show you another relevant piece of code, and that's here in our service. So like, So the service is, if we go back to the architecture diagram, the service is the outermost part of the node. It contains stuff like our SHA-3 proof of work consensus algorithm. And so I have this helper function here called build inherent data providers. And here's how it works. It creates an empty one, and then it registers 2 new providers. So I call providers.register provider, and I do the timestamp one, and I didn't write any of that. I just grabbed it all from Substrate. So this is totally standard. And then here's the next one that I did, which is where I register the provider that comes from my block author inherent. So you can see here, I'm calling my like inherent data provider. That was the thing I implemented that I just showed you guys. And then like, okay, fine, that's a helper function. It returns some inherent data providers. Well, here's where that thing gets wired in. When I create my proof of work import queue, I have to give it some inherent data providers. So like exactly where it's wired after that, I'm not sure, but this proof of work code that comes from Substrate is expecting me to give it some inherent data providers. And as part of the mining process, or more generally as part of the authoring process, it uses these inherent data providers to put the inherents into the block. That's definitely as much as I know. That was a good question, Keon, thank you. Okay, cool. So I guess maybe I'll show you the issuance part next. Issuance is simpler because it's not a whole palette, unlike block author. But in some ways it's similar. So like we start by having this trait, and the trait has 2 type parameters, and they're just like, it's like what type are you using for your block number? So I think in this chain it's a U32. And then the next one is like what type are you using for your balance? And this trait is general enough that it could be used for the account-based model also, but we're using it for UTXO here. And in our UTXO palette, our balance type, or I think we called it value in UTXO, is U128. So here I do some of those like trivial implementations again. Like I think actually I learned this from you, Kian, when you were telling me about transaction fee or transaction payment palette. Like it's really nice to always be able to turn these features off. So if you use unit, then you get no issuance, very easy. And we also did that for block number type U64, just returns 0. But that's not the one we're using right now. We're not using this simple unit one. We're using the one called Bitcoin halving. Let me just show you that. So like we could have set our issuance to be unit, and then we just don't get any, and everything still works fine. Then the block rewards are only whatever comes from transaction fees. But since we have this thing that comes from the issuance, I don't know if I think it's not called a crate, the module, I guess, from the issuance module called Bitcoin halvening. So here it is, it's a unit struct, which means it doesn't have any fields attached to it. It doesn't carry any data. And here's where I implement that issuance trait for Bitcoin halving. And we give it these type parameters. That's our block type and our balance type. So fine, that's all great. And then we provide this issuance thing, and we say, here's how it works. We count up how many halvings we should have had so far. And the way you know how many halvings you would have needed is you take the block number, whatever it is, whatever block we're on, and you do integer division by the halving interval, which or you can see my citation here. This is basically copied directly from Bitcoin ABC. But anyway, so you take the 210,000 blocks, and so if we've halved more than 64 times, we return 0. And this is because if you've halved that many times, then you're going to be down. You've integer divided enough times that the issuance is going to be 0 anyway. But in the more general case where we haven't halved enough times to be all the way down to 0, then we do this. We take the initial issuance, which is 50 tokens per block, just like Bitcoin. And then we do this bit shift operation for however many times we've halved it. So like, just in case you're not as familiar, like if you shift a binary number to the right by 1 bit, that cuts it in half. And it's just like if you take a decimal number and shift it to the right by 1 digit, it divides by 10. And then we convert it into the right type, which is U128. So that's how the issuance works. If you wanted, you could also do something like this. You could do like pub struct constant issuance, and we could even give it a field here, which would be like U128 in this case, and then we could like impl issuance U32, U128 for constant issuance. And then we give it the one function, which takes a block and gives back our token value. And so, you know, like whatever it is, I guess it would be like self.0 in this, or self.0. So then, you know, like whatever, whenever you create an instance of this struct, you give it, here, I'll even do one. Wait, how would I do that actually? I think that would happen over here. So I would want to do constant issuance. And then, oh, this is actually funny. I always struggle with this because I was really tempted to put a type in here, but that isn't quite right. I wanted to put an instance and I need to put a type. So I think this is what I need to do. This parameter types trick, and I'll make a constant of like issuance, and it'll have type U128, and it'll be equal to like, let's just say 50 tokens per block forever. So, so I was like a tiny bit wrong here. This can't be, it can't take a field like that. It has to be a type. So instead I have to give it a type parameter, and I'll just give it like a issuance value maybe. I'm gonna probably skip the rest of this because I won't be able to get it to compile in the right amount of time, but I'll post it in the seminar channel afterwards. But the punchline is I'm gonna want to do something like this, where I pass in this like type parameter into my constant issuance. And I think that will work. Oh yeah, I would need to give it like a trait bound, which is gonna be like get U128 or something. So here's the finished version. It's really close to what we did in the seminar. The bottom is the actual constant issuance struct and trait implementation, and the top is what goes in your runtime aggregation file. I don't want to waste our last couple minutes trying to debug that, because there's another interesting part that I want to show here. And that is the difficulty adjustment. So in any proof of work node, there's this notion of difficulty, which is to say like, how low does my block hash have to be in order for it to be considered valid? And meeting the difficulty is how you show that you've properly mined a block. And a few weeks ago in seminar, I can't remember if it was like 2 or 3 weeks ago, I showed you guys this really simple, like basic proof of work algorithm. And it was naive in the sense that it just had a constant, like a constant difficulty. In fact, I have that code here too. I can show it again. So this is my POW implementation, and there's actually 2 different POW algorithms in here. This is the first one, minimal SHA-3 algorithm. And you can see that for the minimal SHA-3 algorithm, all I do is I say like, okay, the difficulty is always 1,000,000, end of story. If you have a bunch more mining power, blocks are gonna come fast. If you lose a bunch of mining power, blocks are gonna come slow. So that's definitely not very Bitcoin-like. So below, I have this other one. It's not called minimal, it's just called SHA-3 algorithm. And the way that this one works is when I ask it like, okay, SHA-3 algorithm, what difficulty am I trying to mine to? It actually calls into the client via a runtime API, and it asks for, what is the difficulty according to the runtime? So maybe I'll show my diagram again. Right, so here's the difficulty palette, and it communicates with the SHA-3 POW consensus, that's what I was just showing you, through this runtime API called difficulty API. This is super analogous to what Nicole showed us earlier, where the UTXO palette communicates with the transaction pool through this transaction pool API. So any runtime API, just in general, like these yellow trapezoid things, these are ways for the outer node, stuff that lives in the pink part of the node, like the transaction pool or the SHA-3 POW consensus, to call into the runtime and say, yo, runtime, tell me some data that I need. So it could be like the transaction pool saying, hey, runtime, tell me if this UTXO spend is valid, so that if it's not, I can throw it away and not waste everybody's time. Or it could be the consensus algorithm saying, hey, runtime, tell me what the next difficulty is so that I know I'm mining valid blocks. And so that's what we're doing here in the full POW algorithm is we're calling into this difficulty method, specifying the parent block. Like specifically, we want the difficulty as established in the last valid block. And then we start mining. So the question, I guess, is like, okay, it's cool that we can call into the runtime, but like now that we've done that, now that it's wired up to the runtime, like what actual logic is the runtime doing? And that happens here in this difficulty.rs palette. And so you might have heard me talk about this project called Kalupu before. It's another proof of work chain based on Substrate that Wei Tang wrote. And this is totally stolen from him. So like, details about the mathematics and the calculations, I can't answer that, but like high level, what this is doing, I can answer that. So it has this struct that you can see, it's called difficulty and timestamp, and it just has two different fields. One is the difficulty and one is the timestamp. And so what we're gonna do is we're gonna keep track over the last 60 blocks, we're gonna keep track of like, what was the difficulty of this block and what was its timestamp? And its timestamp is basically a surrogate for saying, how long did it take to mine? Because our goal here is that we want to have a constant block time. We want like in Bitcoin, it's 10 minutes. That I didn't put in here because that's way too slow. But we want to have our blocks constant at like maybe 4 or 5 seconds or something like that. And so we're going to use all these 60 data points over the last 60 blocks and do some math on them to say like, okay, it seems like blocks are getting really fast. We better raise the difficulty. Or it seems like things are really slowing down. We must have lost mining power. We better lower the difficulty. So this difficulty adjustment palette has a couple different associated types, just like the other ones we saw. And flipping back to the architecture diagram, you can see it depends specifically on the timestamp palette. Well, that makes sense. We just said we wanted timestamps, so that's how that works. That's this one. It needs something that can provide it with a notion of time, and so we've just used the timestamp palette for that. And then the rest of these are just constants. You know, they use this get trait because they technically need to be types. That was the thing that suddenly tripped me out in the issuance example earlier. And then but these are all basically just like constants. So like, yeah, what do you want your target block time to be? How much damping do you want? Damping is the thing that says like, okay, if blocks suddenly got way faster, we might not want to make this like overreactive sudden adjustment in the difficulty because like mining blocks is probabilistic. Every once in a while, you're going to get a really fast block or a really slow block. And if you make these drastic changes to your difficulty, you're probably going to regret it. So there's a damp factor. There's also a clamp factor. That just prevents it from going below a minimum and above a maximum. I don't really know more than that. And oh yeah, and here's the maximum and the minimum. So anyway, the storage items in here are this: past difficulties and timestamps. And although it looks nasty, it's not that bad. It's an array. It's 60 elements long. And it's an array of options for difficulty and timestamp. So basically, it's an array, 60 elements long. It has 60 of those structs that we looked up above, difficulty and timestamp. Now, it needs to be an option, and that's just to handle genesis, because at the beginning of the chain, you won't have 60 blocks back, and so they'll all be none. And then it's also hard to read because there's a bunch of type parameters that you have to put in there. But that's all it is. And then we also have this storage item that is the current difficulty. And then we have a storage item that's the initial difficulty. And that basically just means like at Genesis, what's our difficulty going to be? So yeah, I'm definitely not going to go through all the logic because like I said, I don't understand it, but this is the math. And I think the next interesting part to show you is where we wire that into the runtime. So we already looked at how we like implement our UTXO trait and we wire it together with block author and we wire it together with issuance. But interestingly, we didn't have to wire it to difficulty. Difficulty is a thing that just works on its own. It's like a separate piece of runtime logic. It's independent of who's spending transactions and all of that stuff. So here's where we implement the difficulty trait. First of all, we have to give it a time provider. That's where we give it timestamp. So that's this line that I was talking about. And then we give it all of these associated types that like are just constants. And for some reason, I'm not seeing, I thought I was going to see parameter. Oh, it's collapsed. Duh. There we go. So here's where I set up all those constants. So like our target block time is 3 seconds, 3,000 milliseconds. These I just stole from Kalupu. I don't really know what good values are there, but those seem to be working. And so like maybe I'll just show this. So like our chain's still running. It's 600 and some blocks deep. And if I go over to the UI and I look at the, oh, where's difficulty? Oh, not on extrinsics, chain state. So if I look at the difficulty adjustment palette and I look at like what's the current difficulty, like, okay, it's at 4,400 some. We just got a new block and it adjusted slightly. And so like we'll wait for another block and it adjusted again. So it looks like it's adjusting downward, which means the difficulty is getting easier, which must mean our blocks were like a little more than 4 seconds long. Yeah, it actually looks like pretty stable. So we must be around the right time. Oh, actually, it'll be interesting. Like, let me kill this and purge my chain. And I think the difficulty starts at 3,000. If I look at my chain spec again, I showed you guys earlier, this is where we initialize like who owns what UTXOs. Well, this is where we initialize what the difficulty is. So apparently the initial difficulty is, 4 million. So when I start my chain again, oh, whoops. Oops, difficulty. So it started at 4,000. It looks like we've missed one adjustment. And then every time a block comes out, it's gonna adjust. Oh, and you can see like blocks are taking a really long time right now. So it'll probably adjust accordingly. Yeah, it adjusted downward again, because blocks took a long time, downward again. So, okay, I think that is pretty much what we had planned to cover. So at this point, I'll just open it up for any questions or comments that anybody has.
Thank you so much. That was super awesome.
Yeah, you're welcome. Good to see you at the seminar, David, and everybody else too.
Back.
See you guys later. Good
Thank you.
chatting. See you next week.
Thanks, everyone.